This video is about the work kinetic energy theorem. This is a really important and honestly ultra basic theorem that connects a very special word in physics called the work and another very special concept called the kinetic energy. So this video is going to be a little bit of an exploration that's going to start from very basic kinematics. And I'm going to take kinematics, I'm going to sprinkle in a little bit of Newton's second law, a little bit of what's called the vector dot product. So this is a little bit of mathematics actually. This is some very basic physics that you've been learning about, Newton's second law. And this is the relationship between variables like acceleration and velocity and time and displacement. So we're going to mix these things up and we're going to actually get the work kinetic energy theorem. Or we're going to get a mathematical or a physics statement that we can identify the work kinetic energy theorem in. Yeah, I hope you get something from this video. So the kinematic ingredient is this one. It's one of your constant acceleration equations. So for the case of constant acceleration, there's an equation that you can get. It says that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. It's called a delta x. And this kinematic ingredient is only true for constant acceleration. So what's interesting about this is the case in one dimension. This is for one-dimensional motion, except for that's not actually true. It's true in each of our 3 space dimensions separately. So this, let's say, is the x direction. So here obviously is an x, but this is the x direction acceleration. So this is the x direction. But it's also true in the y and the z. So in the y direction, it would look like this. So v final sub y squared. So this is the y direction final component of the velocity squared, just the y component. Here is the initial. So doing the y direction, the final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus, looks just like the x except for you make the x's look like y's. So 2 times the acceleration in the y direction times the displacement in the y direction, and there is the z as well. And if you had a 4-dimensional universe, then you add another one for the 4th dimension, whatever you call it. So 2az delta z. Okay, so this is the y and the z. For a constant acceleration. So the acceleration is a vector. It's the x component times the x direction I hat plus ay j hat plus az k hat. So ax is here, ay there, az there. And the velocity similarly. So there is a velocity, it's vx I hat plus vy j hat plus vz k hat. No big deal. That's the velocities. So let me just show you something real quick. So let's use the vector dot product. So far so good, but I'm feeling inspired. I'm going to mix a little bit of this mathematics up and just see what I get. So if I take this velocity, I could look at the final velocity vector, right? So I'll just go in and put VF, VF, VF. So this is the final velocity vector. And what if I did this? So what if? So V final dot V final. So this is the vector dot product. And you know how vector dot products work out. I hope you do. If not, you can go review. But what this does is it just takes the x component and squares it, adds it to the y component squared, and the z component squared. That's what v final dot v final is. And just because I'm curious and I'm inspired, what is v initial dot v initial? This is v initial in the x direction squared plus v initial y direction squared plus v initial z direction squared. So interestingly, like vf.vf is this business, vi.vi is this business, and if I look at what I've got here, these three things are on the left-hand side of the equal sign. They are each individually equal to this combination of these three things, which are here, plus something that's kind of weird, where I've got displacement pieces and acceleration pieces right here. So what I'm going to do is, because I'm inspired, I'm going to go and just take these three things and I'm going to add the left-hand side all together. So it'll be this plus this plus this. And because this was equal to this, and this was equal to that, and this was equal to that, the sum of these three things is equal to the sum of these six things. So I'm going to go and write it this way. If I add all of these things together, then I still get an equal sign because of these three separate equal signs. So adding the left-hand side together, that's just vf.vf. Like this. And if I take the, on the other side, after adding it together, I'm going to get vi.vi, because that's what those three things add up to be. Like this. And then these three things, let me just put them here. So this is plus 2 times, and then ax delta x plus ay delta y plus az delta z. It looks like an x component of acceleration times the x component of something that we called the displacement vector. So I'm writing the displacement vector down. So here's the displacement vector. And you can imagine that if I took a dot delta r, the vector dot product of a and delta r is equal to ax delta x plus ay delta y plus az delta z, like this. So just because I'm inspired, what the hell, I know what dot products do. I'm looking for a shorthand way to remember all three of these directions together, and I have ended up writing down this right here. So 2, this is a 2. So twice the A vector dotted the displacement vector, like this. Okay, so let me rewrite what I've written, but know that this comes from kinematics. So far, this is all kinematics and the dot product, nothing else. But I told you earlier that I'm going to use Newton's second law. I'm going to sprinkle in some physics. This is, quite honestly, this is sort of modeling with mathematics, where acceleration, velocity, and displacement are related in a particular mathematical way, function way, with derivatives and integrals. This is a vector dot product piece of the puzzle. It's just some, honestly, this is kind of like a geometric thing to say. Yeah, it's about vector spaces and how vectors can combine in this particular kind of product. But this is not physics, this is not physics, but this right here, this is physics. So I'm going to go and use some physics. Newton's second law is not about velocity or displacement. Newton's second law is not really about dot products either. Newton's second law, strictly speaking, all that this is the relationship between force, mass, and acceleration. So the only place that Newton's second law is going to go and sit is in my judgment call of how to understand what this expression has to do with force and mass. So let me rewrite this on the next page. So I'm just rewriting that expression. Oops, yeah, plus 2 times the A vector dotted with the displacement vector. Right, so that's just a rewrite of the equation from before. So I know that let's inject some physics